So 1.6, this is all about three formulas really, the Pythagorean theorem and the distance formula and the midpoint formula. So these three things are we're gonna be able to do quite a bit with them. But for right now, we're just gonna focus on kind of using them to solve relatively simple problems. Pythagoras, this is a artist drawing of him, Pythagoras of Samos. He's just a famous mathematician and philosopher. These are around the times of his life here. A lot of things are attributed to him, but obviously it was a really long time ago. We don't really know how much to attribute exactly to him, or more likely people that worked with him came up with a lot of these things too, or they existed before. Yeah, so let's go ahead and dig into these three things. I'm assuming you're already somewhat familiar with some of them, and others were actually on the summer homework. So here's a little warm up to get us thinking. It says, how far will Jack climb to get to 0? So Jack is the skeleton, if you're not familiar with Nightmare Before Christmas, and 0 is this little ghost dog. So how far will he climb along the ladder? So this is a little Pythagorean theorem problem. So if you're unfamiliar with the Pythagorean theorem at this point, I'd be surprised if everyone was completely unfamiliar, but remember, anytime you have a right triangle, which we have right here, right? This is a right angle, and we have a nice triangle formed by the ladder and the ground and the building. We know that there is this formula, a squared plus b squared equals c squared. So go ahead and try this problem. See if you can figure out the length of that ladder. Feel free to throw your answer into the chat if you're wanting me to, oops, I'm gonna look at that, or just so that I know people are doing it. Seems a little big, right? Seems like you're probably on the right track with that number. At least close. Yeah, okay, I'm seeing that. Yeah, okay. I'm seeing some numbers that are certainly along the process of the solution, but not really the solution here. So I'll give you like one more minute, and then I'm gonna go ahead and start setting it up. Okay, so I'm seeing some answers sent to me. They're really close here. A couple good answers. Yeah, so if we look at our right triangle here, whenever you're setting up Pythagorean theorem, the one that's really important is this C. A and B are interchangeable. Doesn't matter which side is A and which side is B, but C is very, very important. C always has to be what's called the hypotenuse. And we'll get more into depth of that, but the hypotenuse is always the longest side, and it's always the one that is across from the right angle. So wherever your right angle is, if you go across the triangle, that's always has to be, this is our C when we're filling in the Pythagorean theorem. That's kind of the most common mistake people make, is they aren't substituting those in the right spots. So C always has to be the hypotenuse. It's always across from the right angle. It's also always the biggest side. And so I'm seeing a lot of people got this to be 13, which is correct. These three numbers, 5, 12, and 13, are a common Pythagorean triple. There's not a lot of whole numbers that work for the Pythagorean theorem. Well, technically there's an infinite number of them, but they're not very common. You know, we have to start getting into really, really big numbers. As far as relatively small numbers, there's not that many that are all whole numbers. A lot of times we're going to at least get one decimal in there or one radical involved. So 5, 12, 13 is a pretty common one you'll probably see show up a lot of times because it's nice whole numbers for our answer. Some other ones are 3, 4, 5, 6, 8, 10. These are all just some common Pythagorean triples that are whole numbers, and there's more too, but there's not that many. There's kind of a handful. So sometimes once you get real good with Pythagorean theorem problems, you'll see some of these really common numbers show up, especially because we like whole number answers. But anyway, let's set this up. So if we got a squared plus b squared equals c squared, again, a and b, it doesn't really matter. We could call this one a and this one b, or this one a and this one b. It's irrelevant for the solution. A lot of times people will call a the smaller one and b the bigger one, just to kind of have some consistency there, but it doesn't really matter. It's important that we just put these on this side with the a and the b, and c being our unknown. So when we square those numbers, we get 25 and 144, and then we add those together, we get 169. And you might not know your square roots up this high, but if you take the square root of both sides to figure out what c is, you figure out it's 13. 13 squared is 169, so that's our square root. So he needs to climb 13 something, 13 feet, 13 meters, 13 something to get up to 0 in this case. Again, I'm kind of assuming some prior knowledge of Pythagorean theorem, but just to make sure that we're all on the same page, we'll go over it in more depth as well. And this was kind of the easier type of problem with Pythagorean theorem. Whenever you're missing the hypotenuse, it's a little easier, a little shorter, and also we ended up with a whole number, so we didn't have to decide whether we wanted a decimal version or a simplified radical version, because both of those are going to be important for us to understand. All right, let's go ahead and move on past this one. So Pythagorean theorem, we already made use of it, but for any right triangle, doesn't matter how the triangle is oriented, right? It could be like we had before, or it could look a little different as long as it's a right triangle. It has a right angle in it somewhere. The square of the hypotenuse, so that's the long side, that's our c squared, is equal to the sum of the squares of the two other legs. So sum meaning we add them together, and squares meaning we raise them to the second power. There's a lot of really fancy, cool proofs for the Pythagorean theorem. We're not quite ready to do them at this moment, but in the future, when we start doing some proofs, we'll look at how you can actually prove that this theorem does work, because it's a cool one to prove. It's a nice algebraic proof too. We just have to use a little fancy algebra. All right. When you're setting up Pythagorean theorem, or just some vocabulary stuff that goes along with this, right? The side that's really important to identify with your problem is the hypotenuse. That's the one that's significant. The hypotenuse always is the right angle. And again, if you take your right angle, draw an arrow across the triangle, that always has to be the hypotenuse. If you don't put it in for C, whatever you have here, whether it's your unknown or one of the sides you know, you're going to make a mistake. And this is the most common problem people have. So they'll end up with a problem like this, and they'll just assume that if we know that this is 10 and this is 8, they'll just assume this is A and B because those are the two sides we know. But that's not true. 10 has to be the C, has to be the hypotenuse. So when you're setting up a problem like this, if you want to solve for this side over here, this has to be C, and these are A and B. So just make sure you're really careful, identify the hypotenuse in your problem, and kind of start your process from there. We'll do an example of this later on. So as I was saying before, there's a lot of whole number answers or integer answers, but most of the time, if you just pick some random numbers for the sides of your triangle starting off, maybe like 4 and 8, a lot of times your answers are not going to be nice, meaning they're not going to be whole numbers. And there's two ways that we will represent these answers. Radical form, which was on the summer homework, reduced radical form, but I'll go over it again, which is like this. So for this problem, when we do our process, let me write this out, but we have to identify our sides. Our unknown is C, and then these are A and B. It doesn't matter. I'll go ahead and call this A and this B, but A and B are interchangeable. So when we set this up, we're doing 4 squared plus 8 squared equals x squared. That's 16 plus 64 equals x squared. That is 80 equals x squared. So to solve this one, we need to take the square root of 80. That's not going to be a nice square root, meaning that we are not going to be able to get a whole number. If it was 81, we'd be good because the square root of 81 is 9. So we do know this is really close to 9, maybe even something like 8.9 as a decimal. But one of the ways that we do this is what's called simplified radical form. So we can take this radical and simplify it. What that looks like is this. We break up our radical into a product, into two numbers that are multiplied together, but we do it very, very strategically. One of the two numbers that in our product has to be able to be taken as a square root and get a whole number. So I'm picking 16 on purpose because I know the square root of 16 is a nice whole number. So you'll need to remember kind of your numbers that you can take the square root of nicely, our perfect square numbers, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, and we can keep going, right? So we can think of all these numbers that have nice square roots and see if any of them can be used to break down whatever we're doing. So in this case, 16 is 4 squared, so I use that one. 16 times 5, that's the same thing as 80. And then we do it this way. We actually take the square root of that 16. Square root of 16 is 4. It comes out of the radical once we take that square root, and we just write it as 4 root 5. Yeah, when you read this, you would read it as 4 root 5. That's something that people will say verbally with their answer. It means that we have 4 times the square root of 5. And that's simplified radical. So these are really two forms. Sometimes we can just leave it as a radical and not simplify it. Sometimes we can reduce it or simplify it. Generally, reduced is preferred if we can do it. In fact, a lot of calculators will automatically reduce radicals for us. Some scientific calculators anyway will. Like if I just type in the square root of 80 in this calculator, it automatically does that. And your calculator might also. I mean, this one's a little fancier, but a lot of scientific calculators have that. Yeah, so I'm getting a couple questions about where did I get the 5. So what I'm doing to get that 5 is I'm thinking about all the ways that I can break down the number 80 as a product. So if I go through the list, I could do 1 times 80, 2 times 40, 4 times 20, 5 times 16, 8 times 10. So these are all different ways that I can break down the number 80 as a product. And so what I'm looking for at all these products is I'm looking for the largest perfect square number. So 4 squared is 16, 5 squared is 25, right? I'm kind of going through all of my perfect square numbers and I'm looking for which of these numbers shows up in this list. And so when I go through it, the biggest one that shows up is 16. So the number 80 can be rewritten as 16 times 5. That's where I'm getting that 5 from. And so when we do that, we break it up this way, and we're allowed to take the square root of 16 because the square root of 16 is a nice whole number. The square root of 16 is 4. So once we take the square root of it, we kind of take it outside of the radical and we put it in front here. And so this is what's called reduced radical form. I'm not going to be super picky about reduced radical form right now. We're going to kind of keep going with it and keep using it throughout the year. The reason we want to use radical form or reduced radical form is because these two answers are exact. We're not getting a decimal, which is a very, very close approximation. These are exact answers. So if we want to be able to take an answer and move forward with and use it to do something and keep it really, really precise, we would want to keep it in one of these two exact forms. And so that's kind of why we're doing it this way. And then the third way, the one that is also fine, is to just get a decimal. We can literally just plug in the square root of 80 in our calculator and tell it to give us a decimal. And so the decimal I got is right here. It's 8.94427. You can see, right? It's the one that you have right there on the screen. So this is a decimal approximation. It's really important to keep in mind this is an approximation. It's really close, and the more decimal places we use, the more close to exact it is, but it is only an approximation. And at some point, we would want to go ahead and cut it off, right? If we were telling the answer, maybe we would only do it to 2 decimal places. So we might say that, oh, this is approximately 8.94. It's a good approximation, but it's not exact. These two answers above are exact. That's kind of the distinction here, and in higher level maths, we'll probably be taking our answers and doing something with them, and so keeping the exact answer and working with the exact answer is going to be pretty important. All right, so again, familiarity with all 3 of these forms. Make sure you know what they are, even if you struggle a little bit with the reduced radical form. Oh boy, I did not mean to do that. Okay, we're going to keep going on. We'll see where we're at the end of this. I'm going to clear my drawings again. All right, so we're going to go ahead and try this on a graph as well. Yeah, so this is going to be a recorded lesson, and it will go up on Google Classroom. So we can use the Pythagorean theorem to find the distance between 2 points. Because any 2 points you can kind of draw a segment right there, and then you can use the coordinate plane to actually turn this into a triangle as well. So if I get a little tricky here, I can kind of draw a line right here along this x-axis, and I can draw a line right here along this vertical line there, and then I've turned this really into a right triangle. What I want you to avoid is counting units along a diagonal line. This is a temptation a lot of people have. They're looking at it and they're like, okay, it's like 1, 2, 3, 4, 5, 6. Okay, so this is 6. That's not true. This distance is not 6. That gives us a slight approximation. We know it's somewhere close to 6, but it's actually a little bigger than that. 6 units can be counted exactly along the grid, but not at a diagonal or at an angle like this. So since this line segment here connecting C and D is angled, I can't actually use the grid to count that distance, but I can count this distance right here, and I can figure out that this distance right here is 6 units. And then I can count this distance right here also. It's 1, 2, 3 units. So now I have a little Pythagorean theorem problem. Instead of just counting along the diagonal, which is not accurate, I've created a right triangle that I can use my Pythagorean theorem for. Now, it's important to note this distance is our hypotenuse. It's across from the right angle. So when we set it up, we want to make sure that our unknown is the hypotenuse. So we might do something like 3 squared plus 6 squared equals c squared. Going ahead and kind of simplifying this out, we end up with 9 plus 36 equals c squared. Adding those together, we get 45 equals c squared. And then here we have the option, right? Because we know that the last step here to find this answer is going to be to take the square root. So I take the square root of both sides, and I could leave my answer one way. I could say, all right, my answer is the square root of 45. That's not a perfect whole number, so I could leave it right here. This is our radical form. But usually, if I'm going to leave it as a radical, I prefer it to be reduced. So what I need to do here is reduce this. The number 45 can be written as 1 times 45, 3 times 15, 5 times 9, and I think that's about it. That's about the only products I can use. When I look through these numbers, I notice 9 is a good perfect square. 9 I can take the square root of. So if I want to do reduced radical form, I would split this up as 5 times 9. Right? And then we know the square root of 9, the square root of 9 is actually 3. So if I take the square root of that, I can write a 3 on the outside. The square root of 9 is 3. I go ahead and write that on the outside. And so our reduced radical form is 3 square root of 5, or 3 root 5. This is the reduced radical form. And then finally, if we just want to go ahead and get a quick and dirty decimal approximation, square root of 45, plug it in a calculator, and we can get a decimal approximation. I've got 6.708, something like that. I'll go ahead and write out my decimal approximation. We get 6.7. I'll go ahead and round it. That C is approximately 6.7. So all three of these things are valid answers. It just depends on what format we want to give it in. Now, if we just had to pick a single answer for the future for what we might want to be doing, the most common one that will be used in the future in other math classes is going to be reduced radical form. It's exact, it's simplified as much as it can be done. So this is going to be the preferred way to do it, is trying to get it into a reduced radical form. Sometimes we may want to use a decimal if we're trying to calculate the area of a shape and we just want to get an approximation of the area. We may want to use a decimal approximation. So we might do that. Radical form is fine too, but if you're going to use the exact format, you might as well do reduced radical. And if you're going to get an approximation, you might as well do it quick and just use a calculator. So we need to be familiar with both of these answers pretty thoroughly as we're kind of keep moving on in our geometry class. And we'll spend more time practicing reduced radical form here and there, but it's just going to keep coming up, and hopefully we'll start really picking it up. Okay, let's go ahead and clear this, and I can already see that we are not going to finish this, so we might have a bit of a change in plans this week, but that's okay. All right, so we already did this. Those were our three answers, right? Root 45, 3 root 5, 6.708, whatever. Doesn't matter, we just need to choose one of those. Now, the distance formula, that's our second big formula here after the Pythagorean theorem. The distance formula is really the same exact thing as the Pythagorean theorem. It's a little bit tricky to see it, but if you're finding the distance between 2 points, and these are our coordinates right here, you can see the coordinates for A and the coordinates for B. These things, x2 minus x1 and y2 minus y1, those are just tricky ways for us to figure out the side lengths of this right triangle. So x2 minus x1, what that's really doing is it's taking these x coordinates and it's subtracting them, and it's figuring out this side length. That's all that's happening with this x2 minus x1, is it's figuring out that side length and then squaring it, just like the Pythagorean theorem. And then similarly, when we do the same thing with the y coordinates, when we do y2 minus y1, it's taking these y coordinates here, and it's just finding the distance between them. When you subtract two things, you find the difference between them, or the distance between them. So when you do the y2 minus y1, you're just getting this side, and then it's squaring it. And you can see, look, it's just basically doing a squared plus b squared. And then it's taking the square root of that to give us our distance, which is always the hypotenuse. The distance being the hypotenuse of this triangle. So really what's happening here is we're saying that c is equal to the square root of a squared plus b squared. It's kind of turning our Pythagorean theorem into a little bit of a more of a plug in your numbers and calculate the solution. But it's different because we're not starting off with side lengths this time. Like before, we were starting off with the side lengths of our right triangle. What we're starting off with now is we're starting off with the x and y coordinates of a particular point. So the distance formula is a little more useful when you just know the coordinates of some points that you want to find the distance between them. Whereas the Pythagorean theorem is useful when you have a right triangle and you know the side lengths and you can figure out the distance between some points using the side lengths there. So both of these two things, the distance formula and the Pythagorean theorem, are based on each other. It's kind of, you can't have one without the other. They really are based on the exact same thing. Now, I want to kind of show how they got all this work, because it's not that clear if I don't kind of walk through the different steps of what's going on. So whenever you have 2 points, so we have 2 points, A, our point A is -2, 3, and our point B is 2, -2. We have to designate one of these as being our first point and the other one to be our second point. It doesn't matter, it won't affect our answer in any way if we call A the first point and B the second point, or we switch that. So for this one, since A is first, I'm just going to call it my first point. So this is my x1 coordinate, -2, and this is my y1 coordinate. You might know this as being similar to like the way you do a slope formula. You might recognize kind of the x1, y1 from your slope formula that you would have learned in Algebra 1. And then here is our second point, so we'll call this our x2 coordinate, and this one is our y2 coordinate. So these are the 4 numbers that we use in our distance formula. So these are the 4 numbers that we're going to be plugging in right here. So as you can see, what's happening when we do this, the x2 is going right there. That's a +2, so that's that one. Minus x1, so minus a -2, so that's what we got right there, minus a -2. Then we squared that whole thing, so we had to do the calculations there, but we're going to square it, plus, and then here we have our y2 coordinate, which is -2, so that goes right there, minus our y1 coordinate, which is 3, so that's where we're getting this, and then again squared. So you can see there's a lot of steps here. Sometimes you're going to have to subtract a negative. You got to be really careful with your integer operations when you're simplifying this, because a missed negative sign or a missed subtraction here can really throw you off. But 2 minus -2 is +4 squared. -2 minus 3 is -5 squared. So now we have our side lengths. We have 4 and 5 squared. 4 squared is 16, 5 squared is 25. It really doesn't matter that this is a negative in here, because once we square it, it won't be negative anymore. A negative times a negative is positive. Add those together, we get 41. This could be our radical form if we wanted to leave our answer as a radical. And this could be our decimal form, 6.4. Just depends on what we want to do with this. In this case, there actually isn't a reduced radical form, because the only way that we can break down the number 41, it's a prime number, 1 times 41. So there are no perfect square numbers that we can use to break this down. So in this case, this is both our radical form and our reduced radical form, because the number 41 is prime. There's no way to break it down. That's a lot of information, and I know that a lot of this was done in the summer homework, but I wanted to make sure that I did teach it. So we're going to finish this tomorrow, and I'm going to have a meeting with Mr. Bechtel about kind of the pacing that we want to do as far as our testing, because we might just end up pushing that back to next week and starting it on Monday instead. So I'll keep you guys updated with that. For when I see you tomorrow, we'll have a plan. We'll do the midpoint formula tomorrow, and then a few more examples, and we'll still start reviewing, but I think the test might be pushed into next week. I apologize for not being sure of things. Just we never know given the circumstances.